Welcome, everyone. Today, we are going to explore a truly fascinating topic in zoology: pearl formation in bivalves. Imagine walking barefoot on a beach and getting a tiny, sharp splinter stuck in your foot. It is irritating, and your body immediately reacts to protect you. Bivalves, like oysters and mussels, experience something very similar. But instead of just swelling, they create something incredibly beautiful. Let us dive in and see exactly how this natural wonder occurs. Now that we understand the basic analogy of a splinter, let us look at the biological trigger for pearl formation. Bivalves are aquatic animals, and unlike us, they do not have hands to simply pull out an irritating object. When a foreign particle, such as a grain of sand, a tiny parasite, or even a piece of a broken shell, accidentally slips into the space between the animal's soft mantle tissue and its hard outer shell, it causes severe irritation. Because the bivalve cannot remove the particle, it must defend its delicate internal tissues in another way. This irritation is the crucial first step that triggers the entire pearl-making process. Following this initial irritation, the bivalve's body goes into active defense mode. The mantle is a highly specialized layer of tissue whose normal job is to secrete the materials needed to build the mollusk's hard outer shell. However, when irritated by a foreign body, the epithelial cells of this mantle tissue begin to multiply and spread. They completely surround and enclose the trapped particle, isolating it from the rest of the body. This newly formed, hollow cellular structure is known as a pearl sac. Creating this sac is essential because it creates a controlled environment where the bivalve can safely neutralize the threat. With the pearl sac fully formed around the intruder, the actual creation of the pearl begins. The epithelial cells lining the inside of this sac start to continuously secrete a remarkable composite material called nacre, which is commonly known as mother of pearl. Nacre is not just a simple mineral. It is a complex biological composite made of strong calcium carbonate crystals bound together by a special protein called conchyliin. Layer by layer, in concentric circles, this smooth and shiny material is deposited over the irritating particle. Over time, this continuous wrapping transforms a painful irritant into a glowing, beautiful gemstone. Before we move on to the mathematics of how fast these pearls grow, let us see this biological process with a concrete visual example. Here we have a cross-section of a bivalve. At the very top, you can see the hard outer shell, and just below it, the soft, wavy mantle tissue. Notice the dark spherical object in the center? That is our foreign body or irritant. Look closely at how the mantle tissue has completely wrapped around it to form the pearl sac, indicated by the cellular boundary. Finally, you can see the concentric rings labeled nacre, building up layer upon layer around the core. This diagram perfectly captures the biological defense mechanism in action. Now that we have visualized the natural process, it is important to understand why this matters, beyond just biology. Scientifically, this is a perfect example of biomineralization, teaching us how living organisms synthesize complex, hard structural materials. Economically, this natural defense mechanism is the entire foundation of the multi-billion-dollar global pearl industry. Humans have learned to harness this biology by intentionally inserting a nucleus into an oyster to artificially trigger the nacre secretion. This practice, known as pearl culturing, provides vital livelihoods for thousands of coastal communities worldwide. Without this unique biological ability, we would not have these precious gems. Understanding the biology naturally leads us to an important question. Can we predict how big a pearl will get? While pearl formation is a biological process, we can use mathematics to model it. By treating the pearl as a growing sphere, we use this formula. D equals D naught plus 2 times R times T. Let us break this down. D is the final diameter of the pearl in millimeters. The symbol D naught represents the initial diameter of the foreign particle or inserted nucleus. The variable R is the radial rate at which the oyster secretes nacre, measured in millimeters per year. Finally, T is the total growth time in years. Notice the factor of 2. Because nacre is added to all sides of the sphere, the diameter grows by twice the radial secretion rate. If the environment is poor, R decreases, resulting in a smaller pearl. Before we move on, let us see this formula in action with a concrete example. Imagine a pearl farmer inserts a spherical shell nucleus with an initial diameter of 6.0 millimeters. The oyster is kept in a nutrient-rich lagoon, secreting nacre at a steady rate of 0.5 millimeters per year. The farmer leaves the oyster undisturbed for exactly 3 years. We want to find the final diameter. We start by substituting our known values into the growth equation. Inside the parentheses, we multiply the rate of 0.5 by the time of 3 years, giving us 1.5 millimeters of nacre on one side. We then multiply this by 2 because the nacre coats both sides, adding a total of 3.0 millimeters to the width. Adding this to our initial 6.0 millimeter nucleus, we get a final answer of 9.0 millimeters. This means the farmer will harvest a highly desirable 9 millimeter pearl. So we have successfully used the formula to find the final size. But this brings us to another practical problem. What if a jeweler requests a specific size and the farmer needs to know exactly how long to wait? We need to rearrange our standard growth formula to solve for the time variable, t. We start with our original equation. D equals D naught plus 2 times R times t. Our goal is to isolate t on one side. The first logical step is to subtract the initial nucleus diameter, D naught, from both sides of the equation. This gives us D minus D naught equals 2 times R times t. Physically, this left side of the equation now represents the total amount of nacre that needs to be added to the diameter to reach the target size. Continuing from our previous step, we have the total required nacre thickness equal to 2 times the radial growth rate times time. To completely isolate the time variable, we must divide both sides of the equation by 2 times R, which is the annual diametric growth rate. This yields the fraction D minus D naught, all divided by 2R, equals T. Flipping the equation around for clarity, we arrive at our final derived formula. T equals the total required nacre thickness divided by the diametric growth rate. This mathematical rearrangement is incredibly powerful. It provides pearl farmers with a precise predictive tool, allowing them to calculate the exact harvest schedule required to meet the strict demands of the jewelry market. Now that we have derived this new formula, let us apply it to a real-world scenario. A jeweler requests pearls that are exactly 10.0 millimeters in diameter. The farmer uses a 5.2 millimeter nucleus, and the local oysters secrete nacre at 0.6 millimeters per year. We need to find out how many years the farmer must wait. We plug our values into our derived formula. First, we subtract 5.2 from 10.0, which tells us we need exactly 4.8 millimeters of total nacre added to the diameter. Next, we multiply the radial rate of 0.6 by 2, giving an annual diametric growth of 1.2 millimeters per year. Finally, dividing 4.8 by 1.2 gives us exactly 4.0. This means the farmer must patiently wait for 4 full years to harvest the perfect 10-millimeter pearls. We have covered a lot of ground today, so let us review the key takeaways. First, we learned that pearl formation is fundamentally a biological defense mechanism, allowing bivalves to protect themselves from internal irritation. Second, we saw how the mantle tissue adapts by forming a pearl sac and continuously secreting layers of nacre to neutralize the threat. Third, we discussed how this incredible natural adaptability forms the basis of a massive global aquaculture industry. And finally, we demonstrated how we can use mathematics to accurately predict both the growth of the pearl and the exact time required for harvesting. You now have a complete understanding of both the biology and the mathematics of pearl formation.